Imagine having exactly 45 minutes to solve 15 complex logic puzzles that dictate your future. The clock is already ticking. A common reaction is to dive straight into mental math. But under this level of pressure, even a single arithmetic error can collapse your final score. The Bebras challenge tests logical reasoning, clever problem decomposition, and algorithmic design. While most people equate computer science with heavy math, the field is often about finding the path of least resistance through the data. Effective problem solving involves using logic to sidestep manual calculation, which minimizes the chances of a technical error before the work even begins. Let's look at a specific task from the Foundation and Core Olympiad phases, the helmet hook score. This diagram outlines the setup. You have a row of hooks, each assigned a binary value: 1, 2, 4, 8, 16, and 32. Placing a helmet on a hook adds that value to a team's total. For example, Team 1 has helmets on hooks 8, 4, and 2. Team 2 has helmets on hooks 2 and 1. Your objective is to determine the exact difference in their scores before the timer expires. A standard brute force approach would be to calculate each team separately. For Team 1, you would add 8, 4, and 2 to reach 14. For Team 2, you would add 2 and 1 to get 3. Then you subtract 3 from 14 to reach the final answer of 11. While this works for small numbers, relying on manual arithmetic under a strict timer induces a high cognitive load, which often leads to mistakes. Consider what happens if the challenge doesn't stop at 32 and the sequence of hooks continues to grow. Calculating the grand totals of multiple 4-digit numbers within a 3-minute window is difficult to do reliably. As the dataset grows, the likelihood of a simple addition error increases significantly. A strategy that fails as the data scales is an inefficient way to solve the problem. Returning to the original 6 hooks allows us to apply the optimization strategy. Step 1 is to identify the binary pattern by comparing the two teams' datasets side by side. Step 2 involves isolating duplicate values. In this case, both teams have a helmet on hook 2. Since both teams share this value, it contributes 0 difference to the final score and can be removed from the calculation. Step 3 is to calculate the simplified remainder. We are left with 8 and 4 for Team 1 and 1 for Team 2. The math becomes 8 plus 4 minus 1, which equals 11. By eliminating redundant data before processing, you preserve critical time and reduce cognitive load. This is the core of computational thinking. Before you process data, you optimize it. Step 1. Identify the binary pattern within the dataset. Step 2. Isolate and cancel any duplicate values. Step 3. Calculate the simplified remainder. When you move away from raw mental math to systematic optimization, you are no longer just solving a puzzle. You've stopped acting as a human calculator and started thinking like an algorithm. Best of luck in the challenge.